Hello, today I'm going to be talking about section 4.8, which is titled Complex Numbers. This is the very last section of the chapter before our next quiz that is involving quadratics using factoring, completing the square, and the quadratic formula. And we're also introducing this idea of a complex number. And there are two learning targets. The first one is to identify and perform operations with complex numbers. And the second one is to find complex number solutions of quadratic equations. And I'll give more examples of these as we go throughout this video. First thing I want to introduce, though, is that sometimes when we have a quadratic equation, we will have no real solutions. I introduced the idea of using the discriminant, which is b squared minus 4ac. When we solve for this in our quadratic formula, if we get a solution that is less than 0, that means that we have no real solutions. And an example of this would be like taking the square root of a negative number. Square root of a negative 2 does not give us a real solution, and the square root of negative 3 doesn't either. The square root of negative 4 also does not give a real solution. So the square root of any negative number is not a real number. So a way we can help simplify these expressions with negative numbers underneath radicals is by introducing something that's called an imaginary unit. An imaginary unit is what I will also use as the letter I, and that is equal to the square root of negative 1. If we square both sides of our equation, we get the formula I squared is equal to negative 1. So there is an imaginary number whose square is negative 1. Now let's take, for example, the square root of 18. A way we can better simplify this is by splitting up our radicals just like we're used to, and we'll split them up into factors where one of them is the square root of negative 1, and it is being multiplied by the square root of 18. Now, using our imaginary units, I is equal to the square root of negative 1. So instead of writing negative 1, we can replace it with the letter I, an imaginary number. This helps rationalize our number and simplify it. The square root of 18 can be split up into the square root of 9 and the square root of 2. 9 is the largest perfect square from the factors of 18. The square root of 9 simplifies to equal 3, and the square root of 2 is being brought down. When I write my solutions, I like to write all of my numbers first, then my imaginary numbers second, and the radicals last. If you choose to write the I first and then the numbers, that is fine, as long as I know that these are all being multiplied. And this is the simplified solution of the square root of negative 18. The next thing I want to introduce is something that's called a complex expression. A complex expression is either a sum or a subtraction. It could be a minus, where one of the numbers that are being plus or minus is real. It could be any number, 1, 2, 3, 4, 5, something that is not imaginary. And the other part includes an imaginary term. B times I is an imaginary part of this expression. Let's take, for example, these two expressions that are being subtracted that are imaginary. This is in the A minus BI form, and this is in the A plus BI form. We can look at our like terms, which are the numbers that are by themselves, and subtract them. So 5 minus 2 gives us 3. And then if we look at our other like terms, which are i's, negative 3i minus a positive 4i, we get a negative 7i. This is the simplified solution of this expression. I'm treating my i's just like I would with my x's. I'm combining like terms, where all of the purples are like terms, the numbers by themselves, and all of the greens are my like terms, all of the imaginary parts by themselves. We can take this one step farther by using FOIL and multiplying two complex expressions together. So the first one's multiplied. 4 times negative 1 gives me negative 4. Then the outsides multiplied, 4 times negative 2i gives me negative 8i. Then the insides being multiplied, 3i times negative 1 is negative 3i. And then the last ones multiplied, 3i and negative 2i, give me a negative 6i squared. Combining my like terms with the i's together, negative 8 minus 3 give me a negative 11i. And my I squared, remembering what our imaginary unit formula is, I squared is equal to negative 1. I can replace my I squared with a negative 1. So I have minus 6 times negative 1. Multiply these two numbers together. Negative 6 times negative 1 gives me a positive 6. And then I can combine it with my negative 4 to equal a 2. Okay, this is the simplified version of this expression up here in orange. Foiling both of the binomials together, combining my like terms, and replacing my I squared with negative 1. A more complex problem using this is going to bring back the idea of multiplying by the conjugate. Because right now our denominator is not a rational number. We have imaginary parts. We want to get those out of our denominator and into our numerator. So multiplying both the top and the bottom by our conjugate is the opposite of the sign that we see in the denominator. So multiply the top by 1 plus 4i and the bottom by 1 plus 4i. Same thing on top and bottom. Multiplying these expressions on top across, we have 2 for the first. Outside is 8i. Inside is 3i. And the last is 12i squared. My denominator, the first is 1. Outside is positive 4i. Inside is negative 4i. And my last is negative 16i squared. Combine like terms on the top with a positive 8i and a positive 3i to give me 2 plus 11i. And I can replace my I squared with a negative 1. So I have plus 12 times negative 1. Then my denominator, my positive 4 and negative 4i cancel out. And I'm left with 1 minus 16 times negative 1, since my I squared is equal to negative 1. Multiplying and reducing all of these numbers together, on the top I'm left with 2 plus 11i minus 12 over negative 16 times negative 1 is a positive 16. Combining the rest of the like terms with the numbers on top, 2 minus 12 is a negative 10 plus 11i, and my denominator is 17. Okay, this is a very, very long problem, but it's tying in the idea of multiplying by the conjugate, which is always the opposite sign that you see in the denominator, multiplying on the top and the bottom. The very last thing that I want to go through that involves the second target is by looking at a quadratic equation. Now, when solving for this, if we ever get a negative under our square root, we can use the idea of a complex number and factor out a negative number from underneath the radical. Let me continue on and explain what is happening. So the general formula is ax squared plus bx plus c equals 0. So that means my a is 2, my b is negative 3, and my c is 5. Using my quadratic formula, that means that I have positive 3 for a negative b, plus or minus the square root of b squared, which is 9. Negative 3 times negative 3 is 9. Minus 4 times a times c. And this is all being divided by 2 times a. Reduce down what's underneath the radical, 9. And we have a negative 4 times 2 is a negative 8, times 5 is negative 40. All over 2 times 2, which is 4. 9 minus 40 gives us a negative 31. And my denominator is still 4. Okay, from here is where we can factor out a negative 1 inside of our radical. So we have an x is equal to 3 plus or minus the square root of negative 1 times the square root of 31. This is all being divided by 4. So the only thing different between this step and here, which is a little bit extra than what we're used to in the quadratic formula, is that I'm pulling out the negative 1 inside of my radical and making this number a positive. My negative 1 is equal to an I, so that means that x is equal to 3 plus or minus I square root of 31 over 4. And this is your final answer. I'm okay with leaving it like this. You can take the square root of 31 and multiply them together, but right now you're telling me that you have 3 solutions. One of them is 3 plus I square root of 31 divided by 4, and the other one is 3 minus I square root of 31 divided by 4. And I'll explain more in class about when I want you to actually factor out the negative and when I want you to just leave it like this. Okay, thank you.